Hi, welcome to discussion 14. My name is Varun Murthy. I'm one of the readers for this course, and today we'll be going through question 1, streaming for voting. Consider the following scenario. Votes are being cast for a major election, but due to a lack of resources, only one computer is available to count the votes. Furthermore, this computer only has enough space to store one vote at a time, plus a single extra integer. Each vote is a single integer 0 or 1, denoting a vote for candidate A and candidate B respectively. So part A of this question asks us to come up with an algorithm to determine whether candidate A or B won, or if there was a tie. Okay, so votes are being cast, lack of resources, enough space to store one vote at a time, plus a single extra integer, 0 or 1, candidate A or B respectively. Okay, so let's think about what a stream of votes might look like. So let me say that this is my stream. Okay, so it might look something of the form A, B, B, A, A. Okay, so I'm asked to come up with an algorithm that keeps track of the majority element. So here we can clearly see that the majority element is A, because I have A appearing 4 times and B only appearing twice. Okay, so a naive way to go about this would be to keep track of the counts of both of these variables respectively, and then compare them at the end to determine which candidate had more votes. But in this problem, we only have access to 2 integers. So our memory space looks something like this. You have 1 integer there, another one here. So this integer is used to store the votes, the vote. This is current. And this integer is at our disposal. So let's just call this the free one. Okay, so I only really have access to just this 1 integer, right? So how am I going to use one number to keep track of essentially 2 numbers? And the idea that I want to take away or sort of introduce here is the idea of a relative count, right? So let's suppose we have 2 measurements. How do we sort of numerically describe where one measurement stands with respect to the other? For example, let's say that we have 2 cars on a highway. You have the first one and you have the second one, and they're both moving in the same direction, right? The first one's moving at 10 miles per hour. The second one's moving at 12 miles per hour. Okay, so you have 2 different speeds, but if I ask you to sort of describe this situation to me overall, right, and I ask you to condense these 2 numbers into one, right, you could just tell me that the relative speed is 2 miles per hour. And what that means is between these 2 cars and these 2 numbers, 10 and 12, their relative speed is just 2 miles per hour. This number 2 describes how well these 2 vehicles are doing with each other, right? So in this case, it means that the distance between the 2 vehicles increases by 2 miles every hour, right? So let's think about how we can use the same idea of relative measures in this question. Okay, so what if I try to keep track of the number of votes that person A gets with respect to the number of votes that person B gets? Okay, so let me introduce this new variable and let me call it I, and let me say that I is equal to the number of votes that A gets minus the number of votes that B gets, right? Very similar to what happened over here. How we got 2 was that we subtracted 12 minus 10, right? So I'm doing something very similar here, and I'm saying that this that this integer I is equal to the number of votes that A has minus the number of votes that B has, okay? And since I have space to hold essentially another integer over here, this is where my I pops in, okay? So at the beginning of the stream, I'm going to initialize I to 0. Oops. Right? And here's my update rule. Okay? If I see an A, no pun intended, then I'm going to update the I. So I is equal to I plus 1. Okay? Or since this is CS70, I guess this is more appropriate. Oh, CS170, sorry. Else, if I see a B, so if I see an A, as in if I see the vote A for candidate A, or if I see a B, as in vote B for candidate B. The pun was on the I's, by the way. Anyway, so if I see a B, then I'm going to decrement I, right? And take a second to convince yourself that this update rule is essentially keeping track of the relative number of votes for A with respect to B, right? So what is this quantity again? Number of A minus number of B. This is the relative number of A with respect to B. The key word here is with respect to. Okay, so let's go back to our stream over here. So my I starts off as a 0. Every time I see an A, I increment the counter, and every time I see a B, I decrement the counter, right? So I see an A, so this becomes a 1, right? I see a B, so I subtract. And before we move on, let's take a second to actually inspect something here. So my counter just became a 0, right? It became a 0 over here at this point. So if the relative number of A with respect to B is equal to 0, right, it means that both A and B show up an equal number of times, which is true. There's exactly one A and one B. So whenever my counter is equal to 0, because it's a relative counter, it means that whatever element I'm trying to measure, its count, that count is equal to the count of every other variable. Okay? So now moving on, I see a B, so I decrement, it's a -1. I see an A, increment, now we're back to a 0. So I'm over here right now. And clearly you can see that since the time we've started until now, there are exactly an equal number of A's and B's. So moving on, I see another A, so that's a 1. And I see another A, and that's a 2. And now I finish. I'm over here. Okay? So I finish with I equaling 2. And this means that number for A minus the number for B is equal to 2. So number of A is equal to number of B plus 2. So number of A is greater than number of B. And this happens if I is greater than 0. And from what we just established, the number of A is equal to the number of B if I is exactly equal to 0, right? And number of A is less than number of B if I is less than 0. Okay? So this is how we can use the idea of a relative count to keep track of the majority winner. All right. So now let's move on to part B. Consider now an election which has 3 candidates, so 0, 1, and 2, and say that we have a winner only if a candidate receives more than 50% of the vote. Otherwise, there is no winner. we're given another integer's worth of storage, come up with an algorithm to determine the winner if there is one. For simplicity, your algorithm can output any of the candidates in the case that there is no winner, not necessarily the one with the most votes. Okay, so once again, let's think about what a stream might look like. So in this case, we have 3 candidates. So a stream might be 0, 1, 1, 2, 1, 1, 0, 1, 2. Okay. So here clearly we can see that the number 1 appears 5 times. So it is the majority element. So how would we actually identify 1 being the majority element? Okay. So let's think of a really naive approach in which we keep track of the number of occurrences of just one of these elements, right? So I have votes numbered 0, 1, and 2. So how about, for simplicity's sake, I just keep track of the number of zeros, okay? So I have access to a third integer, right? So let me say that my first element, whatever my first element is, let me set that equal to w, right? And like before, I have a counter I, which keeps track of the relative count of 0, in this case, with respect to every other element. Okay, so just to recap, I'm setting w equal to 0 because it's my very first element, right? So whatever my first element is, I'm gonna, hold that, and I'm gonna say, well, how many times does this number appear in the stream with respect to every other number? Okay, so that's what's gonna happen now. So I'm gonna count the number of times 0 appears in the stream with respect to every other number. So we can assume that we have zeros and non-zeros. So at the very first vote, I have 1, 0, and then I have a bunch of non-zero elements. So I have 0, minus 1, minus 2, minus 1, minus 2, minus 3, minus 4, right? And then I see a 0, so this increases to minus 3. Oh, my bad. This is a minus 3. I see a 0, this increases to minus 2. I see 2 non-zero elements, so we go down to minus 3 and minus 4, okay? And what this means is that we have 4 more non-zero elements than zeros, which is true because here we have 1, 2, 3, 4, 5, 6, 7. Sorry, it means that we have 4 plus 1, 5. We have 5 more non-zero elements than zero elements. This is because we have 1, 2, 3, 4, 5, 6, 7 non-zero elements. So we have 7 non-zeros. And we have 2 zeros. Okay? So once again, let's think about what happened when our counter was equal to 0. That's over here. Right? So at this point in time, what happened was that the number of non-zero elements exactly equaled the number of zero elements, okay? Which means that there is no majority element because their counts are all equal to each other, or their counts are both equal to each other, right? So at this point in time over here, we don't know what's going to happen with the rest of the stream, right? All we know is that at this moment in time, there is no majority element, okay? So the reason why this algorithm is kind of naive is because it's not changing w, right? So I'm setting w equal to 0 because I'm assuming that 0 is going to be the majority element, and then I'm counting the number of times that it appears with respect to the other elements, right? But a smarter algorithm would actually change my assumption on w once this count hits 0. Because once the count hits 0, it means that there is no longer a majority element. So me holding on to 0 and assuming that it's the majority element is not going to help me very much. So what I should be doing instead is resetting W to whatever next element we have in the stream, which in this case would be a 1, right? And then counting on from there. Okay? So just to recap, what's happening is we're taking the very first element of the stream, and we're assuming that that's going to be the majority element, and then we're counting its, and then we're keeping track of its relative count with respect to the other elements, just like before, right? And that works if our assumption is true that this element is indeed the majority element. But if it's not the majority element, we need a way to dynamically change our assumption on W. And this is where having the counter comes in, because when the counter is equal to 0, it means that at that point in time, there is no majority element. And that is our cue to change W, right? So we can essentially start once again. We can restart, refresh, restart, and we can say, okay, now what's my new majority element? So once my counter hits 0, I update W to be the very next element in the stream, and I essentially repeat the process again. Okay? So what this would look like now, this new procedure, would be the following. Okay, so W is equal to 0, right? And in this case, I is equal to 1. And then I see a different element. So while W is equal to 0, I becomes 0, right? And at this point in time, we have no majority element. So let me reset. Now my next element is a 1. So I'm setting W equal to a 1 and I is equal to a 1. And now we're in business once again. Okay? Now I is decremented because we see a 2, so it becomes a 0. Then I see a 1, so I increment once again. I see another 1, I increment again. I see a 0, so I decrement. Notice that because I is positive over here, I still have 1 as my majority element, right? Because let's not forget what I is. I is essentially the number of this element minus the number of every other element, right? So if this number is greater than 0, it means that my W is the majority element. And the same rules apply as over here. Okay? So, where was I? Okay, I is equal to 1, okay, 1, 0, 1, 2, 1. I see another 1, this increments. I see a 2, this decrements. And when I finish, I'm left with W equals 1 and I equals 1. Okay? And this works because I'm saying at the end of my stream, right, from the last time that the elements were all tied, when I was equal to 0, right, from that time till now, I is equal to 1, I have a majority element over here. Okay, now why does this work? Let's examine this in a little more detail. So let's assume that at some point in time, k, I had I is equal to 0. And at time t equals t, when I'm done processing, I have I equals to some positive constant c for some w over here, okay? So how do I know that my answer is correct? Well, when I is equal to 0, it means that everything from t equal to 0, right, till here has no majority element. That's what having an I equals 0 means. If my relative count is equal to 0, it means that I have as many of these elements as those elements. So there's no majority over here, right? So this duration from t equals 0 to t equals k essentially adds no value to me, right? So let me reset, and now let me do the same procedure, and when I finish I have I equals c, which means that in this portion over here we do have a majority element which is equal to w, right? And if w is the majority here and there is no element that is a majority over here, then clearly w is the majority of this entire thing, right? So you have no majority element over here, but you have a w over here, which means that w has to be the majority of both of these combined. Okay, so let's go back to this algorithm. So we said that set w to be equal to the very first element of the stream, and then increment I every time you see that element, otherwise you can decrement I. And then we updated that to be whenever I is equal to 0, reset your w to be the very next element of the stream, right? So what that would look like in pseudocode is if I is equal to 0, then w is equal to the next element. Else, if I is positive, then just apply the update rule. Okay. You might be wondering what happens if I is negative. It's never possible for I to be negative, because as soon as I becomes 0, we are hitting this condition, and then I has to grow, and then it might fall and might be equal to 0 again, but it's never going to be negative because it can never fall below 0. So this is essentially the algorithm to solve part B. Okay, thank you.
My name's Alicia. Varun just did question 1, streaming for voting, on this week's discussion, and I'll be going over question 2, which talks about universal hashing. So before we dive into that, let's revisit what hash functions do and the motivation behind them. The key idea behind hashing is we rely on hash function h to map, let's say, n keys ki to a smaller address space. Let's name this squiggly s, and the size of the address space can be m. So there are m possible values that we can hash to using this hash function h. And to visualize this, I'm sure you also went over this in lecture, but just to visualize, we can have this space of all the possible keys. There are n of them, and as we apply, and we can name this u, I think that was the naming convention, our hash function maps whatever is in this space u to this set m being the number of buckets. So we have a total of m buckets, and each bucket contains the hash value of mapped to the item. In our case is the key itself. Hopefully this is pretty familiar to you. So our goal behind this is, for search, we want our runtime to be proportional to the number of keys per bucket. And our bucket is the hash value for every ki. So how are we able to kind of achieve this runtime? What we actually want is to find a cheap hash such that we have very few collisions for our input. We concluded that the best option is to use randomness. So we pick h at random from a hash family. We'll go over what a hash family is in a bit, but for now we can denote it with this fancy H. So the hash that we choose doesn't depend on whatever keys we take as input. And the implication of having a good hash is that our expected number of keys in the same bucket, I for every I in set M, would be n over m. So think about it as a balls and bins question. Say you had n balls and m bins. Every ball has the same probability of being thrown into each of the bins. The expected number of balls in each bin would be n over m. This is the same exact logic applied here. So with this, we actually end up with a constant, big O constant number of keys. The number of collisions we get is actually constant. And this is very helpful because now our search time is also O of 1 in expectation, which is better than binary search. And of course, some buckets are bound to have more than n over m, which is possible. We have a constant search time in expectation. And our goal today is to construct universal hash functions. And that is question 2 of discussion, universal hashing. So let's just visit this problem. We have a set M denoting a set of values 0 through m minus 1. The first thing that comes to mind is modular arithmetic when I see something like this, because you have the set of integers modulo m. Just a side note, might be helpful later on. For each given hash function or family of hash function, we want to determine if it's pairwise independent, universal, or I guess neither. The problem didn't really define for us what universal is or what pairwise independent is, so we should do that. Okay, let's define a looser definition, universal. So what does it mean for a hash function to be universal? It means for every x, y in this set M, the probability that our hash function hashes x and y to the same hash value is probability 1 over m. And m usually denotes the number of possible values that our hash function hashes to. Okay, I think you saw that in lecture as well. And next, let's define pairwise independent. I wrote k-wise independent here because it's a more general case, but let's take a look at pairwise first. Side note, pairwise is also known as strongly universal because it's a stronger statement than saying a hash function is universal. To be pairwise independent means the probability, the hash value of one input is alpha 1 and the hash value of another input is alpha 2 is less than or equal to 1 over m squared. M defined as the number of possible hash values that this hash function gives you. So to generalize this, what it means to be k-wise independent is the probability that one input hashes to alpha 1 and the second input hashes to alpha 2. All of these are distinct inputs, by the way. And a kth input hashes to alpha k. The probability of this is less than or equal to m to the k. Yep. And two more things that I think we should point out is any k-wise independent hash family is also k minus 1 wise independent. It's kind of like induction. And lastly, this kind of refers to what I mentioned earlier, but pairwise independence is a stronger statement. If like a hash family is pairwise independent, then that implies it's also universal. But a weaker statement cannot imply a stronger one, so the converse is not true. Feel free to pause the video and we're going to dive into the problems now. So given this hash function a1x1 plus a2x2 mod m being a fixed prime, which is a pretty important, I think, statement, we have to determine if this hash function h is universal or pairwise or neither. And the discussion worksheet notes that this hash function basically maps a pair of integers in our set M to a single integer. Okay, let's just get started then. So assume we have distinct pairs x equals x1, x2, and y equals y1, y2. Where x doesn't equal to y, or x1 doesn't equal to y1. a1 and a2 are values that we can choose. So if we were to choose a1 and a2 such that we force x and y to be hashed to the same values. The thing we want to prove here is if it's universal, then the probability of two distinct values hashing to the same hash value, the probability is 1 over m. That's something we want to prove here. So if we were to choose a1 and a2 such that we hash x, y to the same value, assuming that this is true, then how can we express this mathematically? So see how we have the mod operator? This is usually a good hint that we might want to use modular arithmetic. We can write an equation. So a1 x1 plus a2 x2 equals a1 y1 plus a2, or it's congruent to that mod m. Factor out the a1 here as well as the a2 here. When does this equation hold true? Only if a1 is also congruent, is also the same as a2 y2 minus x2 x1 minus y1 inverse mod m. In order for this to hold true, x1 minus y1 must have a unique inverse, since x1 and y1 are not the same. And we know that they do because m here is prime. So what's the probability that this whole expression here, mod m, is the same as a1? Since we only have m possible values, the probability of that is actually 1 over m. So it is universal. And the second part of it is we have to determine how many random bits are needed to choose a function from the family. But what we're actually doing is we're just randomly picking two integers in the range 0 to m minus 1. To represent all the integers in the set m, we only need log m, and we keep track of two integers. We only need two log m bits to choose a function. Let's move on to part B, where we have the exact same function or hash family, except now m is no longer a fixed prime. So now we set m to be 2 to the k, which means it's some fixed power of 2. It is no longer prime, even though we're still in mod m space. So my first instinct tells me that this hash family is not pairwise, nor is it universal. But to prove it, we have to come up with a counterexample. Assume we have x and y again, x being x1, x2, y being y1, y2, and I'm going to assign values to them. So x can be a pair 0 and 2 to the k minus 1, y being a pair of 2 to the k minus 1 and 0. With these inputs, our hash function gives us the following equations. So by hashing x1 and x2, we get 2 to the k minus 1, alpha 2. Actually, let me write it out. And we also have the hash function being applied to y1 and y2, 2 to the k minus 1, alpha 1, mod 2k. 2k being the same as m. So let's examine this function right here. I'll use a different color. Since m has the factor 2 and is thus even, we can look at the other factors in the modular expression to see the implications of that. So let's assume that if a2 is even, we have h of a1, a2, x1, x2 being 0 because it has a common factor with the modulo here. On the other hand, if we have a2 is odd, I'll write out the steps. So 2k minus 1 times alpha 2 equals 2n plus 1. We have 2 to the k minus 1 times 2n plus 1, which gives us 2 to the k minus 1 times 2n plus 2 to the k minus 1, which is 2 to the k times n plus 2 to the k minus 1. So what is this mod 2k? It's just 2 to the k minus 1 mod 2 to the k. And this is the result if a2 is odd. For the second equation that we got for y1 and y2, the same reasoning follows for a1. So how often is a2 even? The probability of alpha 2 is even is 1/2. And similarly for alpha 1. So in the end, we get that the probability that distinct inputs hash to the same values is the same probability that alpha is even, which is 1/2. And that is greater than 1/2 to the k. So the family is actually not universal. And lastly, for part C, we have a new function. No more modular, we map from the set m to set m minus 1. The way I interpret this is you now have one less distinct value. Set m goes from 0 to m minus 1, so your new set only goes from 0 to m minus 2. Different functions, same way of approach. Intuitively, this might seem like it could not be universal because for every single distinct value in set m, we don't have a matching distinct value in m minus 1, but we should still check to see if this function fits our definition of universal one-to-one mapping. Let's again assign x and y that are in 0 to m minus 1 as input. So to calculate the probability that hash values x and y will collide with this function is actually equal to the ratio of the number of functions f mapping m to m minus 1 such that x and y will collide over the total number of functions possible. Seems like the denominator is easier to calculate. How many total functions can we have? We have a total possible number of m inputs and m minus 1 outputs. So our function, which yields the number of outputs, m minus 1, can have a total of m input. So this is actually the total number of function f that maps set m to set m minus 1. Let's fix a collision for hash values of x and y. So let's say that fx and fy, they both hash to value k such that it's some value in set m minus 1. So it can be any number 0, 1 through m minus 2. Since we fixed fx and fy two inputs to k, we now only have m minus 2 inputs where we can map it to anything we want. Similar to the case above, we have m minus 2 outputs. Following the line of logic from the first part, we would have m minus 1 to the m minus 2 functions f such that we yield fx equals fy equals to a particular k. Our only requirement here in the numerator is as long as x and y collides, we would count it. So far, we've only calculated the number of functions for one particular k, so I think we have to sum over all possible values of k. K is some value in set m minus 1. How many possible values can it take on? For all k, we would have m minus 1 times m minus 1 to the m minus 2, which gives us m minus 1 to the m minus 1 functions, such that this holds true. So now we have the probability that two distinct input values will collide with probability m minus 1 to the m minus 1 over m minus 1 to the m, which is 1 over m minus 1. And this is exactly the definition of the universal hash function. M minus 1 is the total number of possible hash values, which again directly implies the definition of a universal hash function. So yes, this f is perfectly fine. And the next part is to determine the number of bits that we need to represent our whole family of functions. So in this case, we actually don't really have a way to represent it succinctly. Instead, we just pick one of the possible m minus 1 to the m functions. In order to do that, we can do indexing and randomly picking an integer, say 1 all the way to m minus 1 to the m. So 1 bit can represent 2 of these indices, so we can just take the log to get m times log m minus 1 bits. Feel free to post on Piazza with any questions you have, and have a great weekend.